Hello and welcome back to our next video in looking at power series representations of functions, and we're still working with variants of the function 1 over 1 minus x. But want to introduce some other things that we can do to power series in general first, and that is that we can calculate derivatives. We can find power series representations of derivatives and integrals of functions as well. And the key is to do what we call term-wise. So we're going to, if we have a formula for a power series formula for a function, we get the power series for the derivative of that function by differentiating each term and adding them up. And likewise, we'll get a power series representation for the integral of a function by integrating each term in that power series. So let me say a little bit more clearly, I hope, what I mean, and that is that if I've got the derivative of a power series representation of a function, that's the same thing as adding all the derivatives of this expression. But we know how to take the derivative of a power function. So we're going to get summation n equals 0 to infinity n times a sub n x to the n minus 1. Now, but notice that when n is equal to 0, I get 0 for my first term, and so sometimes you'll see this written as summation n equals 1 to infinity n times a sub n x to the n minus 1. So this is going to be the sort of the general formula for the power series representation of a derivative of a generic power series. And then if I want to find an integral of a power series, I can do that term-wise as well. So it'd be integrating a sub n x to the n dx. Well, again, that's a power function. I can just anti-differentiate that term-wise. I'm going to get a sub n over n plus 1 x to the n plus 1. And we want to keep in mind that oftentimes, if we're talking about an indefinite integral, we'll need an add a plus c to that. Although we'll see that sometimes it's pretty easy to tell what the value of c is. And so this is our general formula for the indefinite integral of a power series. So let's look at a few examples where we use derivatives and integrals. I've got one problem with derivatives and two problems with integrals here. So if I want to find the power series representation of 1 over 1 minus x quantity squared, we want to recognize that this function is the derivative of 1 over 1 minus x. And let's just go ahead and verify that. I'll write 1 over 1 minus x as 1 minus x to the negative 1. And so I'm going to get negative 1 minus x to the negative 2 times the derivative of what's inside, another negative 1. And so those cancel, or negative 1 times negative 1 is 1. And so I get 1 over 1 minus x squared. So 1 over 1 minus x quantity squared is going to be the derivative of the power series representation for 1 over 1 minus x. But that's just summation n equals 0 to infinity x to the n. And so I'm going to make that be the sum of the derivatives of this. And so I'm going to get summation n equals 0 to infinity n times x to the n minus 1. But we want to remember that, as I said above, we can change that 0 to a 1 because the first term of that sum was going to be 0. And so here's my power series representation for 1 over 1 minus x quantity squared. Now I've got two examples involving integrals. One is our old friend, the inverse tangent function. And so hopefully we remember that the inverse tangent is the antiderivative of 1 over 1 plus x squared. Well, hopefully we can think about this as 1 over 1 minus the quantity opposite of x squared, and which in turn means I can write this in the form summation n equals 0 to infinity opposite of x squared to the n, but then I can rewrite that still as minus 1 to the n x to the 2n. So now I've got an integral of a power series representation of a function, so I can switch the sum and the integral. And I know how to anti-differentiate that. So we get summation n equals 0 to infinity, minus 1 to the n. I raise the power by 1. I divide by the new power. And then I toss on a plus c. But let's take a second and see that we can actually tell what c is going to be in this case. So, sorry, it should be plus c here. So plug in x equals 0. Well, tan inverse of 0 is 0, which means that I need this sum to be 0. But if I'm plugging in zeros for x everywhere, this is all 0. And so I just get c. And so that tells me that c is equal to 0. And so therefore, tan inverse of x is simply summation n equals 0 to infinity minus 1 to the n, x to the 2n plus 1 over 2n plus 1. And we will come back and use this in probably another example or two later on. And I do have something I want to say about this later, that we can actually use this power series to approximate pi. And so maybe I'll talk about that in class one day. And then finally, I've got a rather lengthy example where I'm going to use the alternating series remainder estimate to approximate the value of this integral. I may or may not be able to use the fundamental theorem of calculus to anti-differentiate this, but let's actually try to find an approximate value using power series. So this is going to take a lot of work. So let's just buckle in and see how we can do this. So I'll start by coming over here. We did something with this function earlier, I think, and we saw that I want to write this. Actually, we looked at something similar to this, but it wasn't exactly this. I want to think about this as x times 1 over 1 plus x to the fourth, and that's going to be x times summation n equals 0 to infinity, opposite of x to the fourth to the n, which I'm going to be able to simplify. We've seen something like this before. Summation n equals 0 to infinity minus 1 to the n, x to the 4n plus 1. So that's our power series representation for what we're integrating. So let me substitute that in over here. And I know that I can switch the sum and the integral. Oops, sorry, getting carried away. Minus 1 to the n, x to the 4n plus 1 dx. Now I can anti-differentiate. Add 1 to the power, divide by the new power, and I'm evaluating between 0 and 1/2. So when I put zeros in, I get a whole bunch of zeros. And so what I'm really interested in, what happens when I put 1/2 in, so we get 1/2 to the 4n plus 2 over 4n plus 2. And I'm going to write that slightly differently. I can think about 1/2 to the 4n plus 2 as 1 over 2 to the 4n plus 2. And so this is going to be 1 over 2 to the 4n plus 2 times 4n plus 2. And so this is the sum. This is that integral written as a sum. And so this is a number. It's going to be a convergent series. But I need to figure out what does it approximately converge to? How much do I need to add to get this to within 1/20,000th of its actual value? Okay, well, let's remind ourselves of what we want to do. I want to use, I'm going to use the alternating series remainder estimate, which says that the remainder, R sub n, is less than B sub n plus 1. And if I want to make R sub n less than 1/20,000th, I'll make this less than 1/20,000th to make R sub n less than 1/20,000th. So I need to figure out what B sub n plus 1 looks like. And so let's just do B sub n first. B sub n here, it's my positive term in this series. It's going to be 1 over 2 to the 4n plus 2 times 4n plus 2. So B sub n plus 1 I find by replacing the n's with n plus 1. And if I do that work, 4 times n plus 1 plus 2 is 4n plus 6. And so I've got B sub n plus 1 being 1 over 2 to the 4n plus 6 times 4n plus 6. And so my goal then is to find n so that 1 over 2 to the 4n plus 6 times 4n plus 6 is less than 1/20,000th. But I can take reciprocals here. I'm a much bigger fan of trying to make numbers bigger than a number. So I can say, or make 2 to the 4n plus 6 times 4n plus 6 bigger than 20,000. This is a case for a little bit of trial and error, but it turns out I don't need to do too much here. Let's look at n equals 1. If I put 1 in for n, I get 2 to the 10th times 10. And that number turns out to be pretty big already, 10,240, but that's not bigger than 20,000. So I'm pretty hopeful about n equals 2. 2 to the 14th times 14 turns out to be way bigger than 20,000, more than 229,000. And so that tells me that all I need to do is, if n equals 2 works, then what I'm getting is, so summation n equals from 0 to 2 of minus 1 to the n, 1 over 2 to the 4n plus 2 times 4n plus 2 approximates the integral 0 to 1/2 of x over 1 plus x to the 4th dx to within 1/20,000th. And just to write out those terms, when n equals 0, I get 1 over 2 squared times 2 minus 1 over 2 to the 6th times 6 plus 1 over 2 to the 10th times 10. And so if we just add these three numbers together, that will be an approximation of that integral, and it will know that for sure that's within 1/20,000th of the actual value.